Hello students, good morning. Today we are going to start our first part of general solution, which is known as complementary function. As we already discussed in our previous video that there are two parts in general solution of any higher order differential equation. In the first part of general solution, which is known as CF, means complementary function, there are total 4 possibilities. In this part, we are going to focus only on the first possibility for the complementary function. Let us start our first part of complementary function. As you can see over here, for simplicity, I am considering second order differential equation. On the left hand side, you can see y double dash plus cy dash plus c1y dash plus c2y equals to r of x. Let me recall that this y double dash indicates double order derivative of y with respect to x. Throughout this discussion, we are assuming that y is dependent variable on independent variable x. The c1, c2 are random constants. We are assuming the structure of second order derivative in such a way that the highest order derivative term is with constant coefficient equal to 1. If there is any number multiplied over here, that you can shift on the denominator of this 2. Or else you can directly consider the given differential equation as this. Now let us introduce the differential operator capital D raised to n as d by dx power n. It will help us to consider differential equation into comparatively easy form. Once we introduce the differential operator capital D, the second order differential equation will take this form: d square y plus c1 d of y plus c2 y equal to rx. If we simplify this left hand side, it gives us d square plus c1d plus c2y equal to r of x. Then converting this part into f of dy, it gives us f of dy equal to rx. So this part f of d, it is a random combination of capital D, which is differential operators, and some arbitrary constants. So this will be the formation of our differential equation. This is the first and the most important part of any question of higher order differential equation. This form is also known as differential operator form of equation. Now let us move to the complementary function as a part of general solution of given higher order differential equation. First of all, at the differential form of equation which we already derived is f of dy equal to rx, we need to consider one equation which is known as auxiliary equation. Auxiliary equation is f of d equal to 0. So from this equation we need to consider only this part f of d and we will equate it to 0. Once we equate it to 0, it will give d square plus c1d plus c2 equal to 0. This simply means that it is equation in terms of capital. You can treat this equation as a regular second order equation and you can factorize it accordingly. Now, if I factorize that second order differential equation, there are 4 possibilities for the roots. So Depending upon these four possibilities, we are classifying our complementary function into these four classes. The first case is auxiliary equation is with real and distinct roots. Second case, auxiliary equation is with real and repeated roots. Third case, auxiliary equation is with complex and distinct roots. Fourth case, complex and repeated roots. In this talk, we are focusing only on first case of real roots, which simply means that real and distinct roots of auxiliary equation. So, for example, if we consider a second order differential equation, if we equate it to 0, this equation obtained is known as characteristic equation or auxiliary equation of given higher order differential equation. Now, if I factorize this and if I receive two real and distinct roots, namely m1 and m2, then the corresponding complementary function is denoted by yc of x, and it is given by c1 times e raised to m1x plus c2 times e raised to m2x. Don't get confused in between this c1, c2 and this c1 and c2. This c1, c2 are given in the equation and this c1, c2 are arbitrary constants. There is no relation in between this c1, c2 and this c1, c2 in the c2. You can also assume over here a1 and a2. So this will be the structure of complementary function. Let us consider one example to make this thing clear. Example number 1, find CF for differential equation y double dash minus 5y dash plus 4y equals to e raised to 2x. It can be seen clearly over here that it is linear, it is non-homogeneous, and it is with the constant coefficients. So this is exactly falling in our higher order differential equation, constant coefficient, linear, non-homogeneous equations category. So we can find complementary function as per our discussion earlier. So the first thing is to convert this equation into operator form. So as I told you already that y double dash is simply d square of y minus 5y dash is minus 5d times y and 4y is simply plus 4y. You can write this type of formulation for given differential equation directly, and it is equal to e raised to 2x. Now focusing on complementary function, we need to identify auxiliary equation. So the auxiliary equation over here is f of b equals to 0. So I need to take only this big bracket d square minus 5d plus 4 equals to 0. If I factorize this, I will get two roots 1 and 4. Now you can observe clearly that these two roots are real and they are different from each other. And so the complementary function will take this type of value. It is c1 times e raised to m1x, which is 1 into x, plus c2 times e raised to 4x, which is x. There is no certain rule for the orders of the root. You can consider this 4 in the first position and 1 in the second position. It is also valid solution. Let us consider second example. Again, question is to find complementary function for this third order differential equation. Y triple dash minus y double dash minus 6y dash equals to x raised to 5. Again, repeating the same step. Converting this equation into differential form takes this type of shape. It is d cube minus d square minus 6d of y equals to x raised to 5. Considering its auxiliary equation by f of b equals to 0, which simply gives us d times d square minus d minus x equals to 0, and by factorization we will get three roots. M1 equals to 0, M2 equals to 3, M3 equals to minus 2. Again, let me remind you that there is no certain rule for the orders of these roots. It can be in any order. And so, as these three roots are real and they are distinct, our complementary function will be c1 plus c2 e raised to 3x plus c3 e raised to minus 2. So, with each of these arbitrary constants, there is an exponential function with exponent root. So, it is e raised to 0x over here, e raised to 3x over here, and e raised to minus 2x over here. Let us consider third case or third example. Question is again to find the complementary function for y triple dash minus 3y dash minus y dash plus 3y equals to 0. The operator form of this equation will be d cube minus 3d square minus d plus 3 times y equals to 0. For complementary function, let us consider auxiliary equation by taking f of d equals to 0. Once we consider this d cube minus 3d square minus d plus 3 equals to 0, by factorization, you can convert this into d minus 3 times d square minus 1 equals to 0. And then by considering three roots, 3, 1 and minus 1, as they are real and distinct, the shape of yc will be of this form. c1 times e raised to 3x exponent for first root plus c2 e raised to x exponential function for second root plus c3 e raised to minus 1x exponential function for third. This is how you can consider first part complementary function whenever your auxiliary equation is giving you real and distinct roots. In upcoming videos, we are going to consider real and repeated roots and some complex cases also. You should revise this video, you should pause and ponder whenever it is required, and you should think upon the formation of complementary function in this case of real roots. Thank you.